Why does a tightrope walker carry a long pole? How does a spinning ice skater control their speed? These questions may seem unrelated, but they both have a common thread: the fascinating world of rotational motion. Imagine a tightrope walker delicately balancing high above the ground. The long pole they carry helps them maintain their balance. The pole, with its weight distributed far from the walker's center of mass, has a high moment of inertia. This means it resists changes to its rotational motion, helping the walker stay upright. Now, let's switch gears to the spinning ice skater. When a skater pulls in their arms, they're reducing their moment of inertia, or their body's resistance to changes in rotational motion. With less moment of inertia, they spin faster. This is the principle of conservation of angular momentum. But what exactly is angular momentum? It's a measure of the amount of rotation an object has, taking into account its speed, shape, and mass. Just like linear momentum, angular momentum is conserved unless acted upon by an external torque. Torque, another key player in rotational motion, is a measure of how much a force acting on an object causes that object to rotate. The greater the distance from the pivot point, the greater the torque. This is why door handles are placed far from the hinges. Let's dive deeper into moment of inertia. It's the rotational equivalent of mass, a measure of an object's resistance to changes in rotational motion. Different shapes have different moments of inertia. For instance, a rod, a disc, a ring, and a sphere all have unique moments of inertia. Theorems of parallel and perpendicular axes are fascinating tools that help us calculate the moment of inertia for complex shapes. These theorems state that the moment of inertia about any axis parallel to and a distance d away from an axis through the center of mass is the sum of the moment of inertia for the axis through the center of mass and the product of the mass and the square of the distance d. Radius of gyration, another intriguing concept in rotational motion, is the distance from the axis of rotation at which, if the entire mass of the object were concentrated, its moment of inertia would be the same. For a rigid body, the radius of gyration provides a measure of the distribution of the mass around the axis. In essence, understanding rotational motion is not only crucial for physics students, but also enlightening for anyone curious about the world around them. From the spinning of the Earth to the wheels on a car, rotational motion is a fundamental concept that governs the dynamics of our daily lives. In summary, rotational motion is a fascinating and complex field that governs many everyday phenomena. From the balance of a tightrope walker to the spin of an ice skater, the principles of torque, angular momentum, and moment of inertia play a vital role. Understanding these concepts illuminates the underlying mechanics of our world.